My name is Melanie Beck, and in this session, I'll show you a way to perform document classification in limited labeled data regimes using text representations. I'm a machine learning research engineer at Cloudera Fast Forward Labs. The goal of our team is to make the recently possible useful by identifying the latest research developments in data science and machine learning that hold the most promise and produce artifacts that are useful for practitioners. These artifacts take many forms, including demos and live applications, as well as research reports that walk the reader through the emerging capabilities and technologies. Our research is free and open source, and you can find out more through the links here. Today, I'll be presenting our work on few-shot text classification. Let's take a look at the agenda. I'll start with a brief overview of the method and then jump directly into a demonstration because oftentimes seeing is understanding. Then we'll unpack more of the details and look at results from experiments we've conducted. We'll follow with a discussion of limitations because in our experience at Fast Forward Labs, every method has pros and cons. But first, let's set the stage with the best question of all. Why? Why would we care about few-shot learning? And for me, the answer is simple. Labeled data is expensive, but text classification is ubiquitous. Text classification has become a fundamental component of a variety of applications, from sentiment analysis, topic assignment, document identification, article recommendation, and more. And while dozens of techniques now exist to perform this crucial task, many require massive amounts of labeled data in order to prove useful. However, collecting annotations for your use case is typically one of the most costly parts of any machine learning application, and in some cases may not be feasible at all. Therefore, it's crucial to harness methods that make the most of our data, labeled or otherwise. Before we get too deep, let's review the most typical limited labeled data regimes. Labeled data, or the lack thereof, comes in several flavors. Few-shot learning, for example, is traditionally performed in cases where a small amount of labeled examples is available for each label that a classifier is expected to recognize. Zero-shot learning can take several forms, but the traditional definition is when a classifier is trained on one set of labels, presumably with a significant amount of labeled data, and then evaluated on a different set of labels that it has never seen before, thus zero-shot. Less common is what I'll call on-the-fly learning, wherein classification proceeds with no training examples at all and an undetermined number of labels. The method I'll talk about today can actually perform in all of these regimes. But how, you might ask? By leveraging the intrinsic information contained within the labels themselves, their semantic meaning. Humans do this every day. When we read an article about baseball, for example, we don't need training data to teach us that this article is about sports. And it turns out that modern text embeddings can perform a similar function. At a high level, we start with an embedding model, which converts text into dense vector representations. We use this embedding model to generate representations both for our document and each of our potential labels. If we plot these representations in latent space, we can compare the document's representation against each of the label representations. Classification proceeds by assigning the document that label which is most similar to it. In other words, closest to it in that latent space. To drive it home, let's see this method in action, demo time. You can check out this demo for yourself by going to our GitHub repo, and I'll have a link at the end of this session. In this demo, we have several examples of news articles from the AG News dataset. And here, we have a list of possible labels that each article could be assigned to. Below that is a chart that shows how similar each of these labels is to this news article. The most similar label is assigned to that article as its label. In this case, we have an article about supernovas, and the sci-tech label is the most similar, and that makes sense. But what if we needed to add a label? I particularly like this news article about supernovas because I used to be an astrophysicist. So maybe instead of sci-tech, I want to classify into an astronomy category. So I can add my new label and hit run, and voila. Now astronomy is the most similar to this article, and that makes sense. This is what we call on-the-fly learning. The model underneath has not been explicitly trained to classify news articles into categories like astronomy. In fact, it hasn't been trained on any of these labels at all. But embedding models have been trained to glean the semantics, syntax, and context of words, allowing them to act as off-the-shelf, on-the-fly classifiers. And speaking of on-the-fly, the obvious question is, what embedding models can we use for this? The answer in this particular case, for that demo we just saw, is SentenceBERT. BERT has been a popular embedding model for several years now and excels at providing contextual representations for words. Its cousin, SentenceBERT, is optimized to embed, well, sentences, and is specifically designed for tasks like semantic similarity search and clustering, tasks that typically rely on cosine similarity to find like documents. We explored using SentenceBERT as an on-the-fly classifier for a couple of data sets, and here are the results. While they may not seem too promising, keep in mind that SentenceBERT is not trained as a classifier and has never seen these examples or labels before. Additionally, while tepid, these results are still stronger than random chance baselines, so we're on the right track. But we can do better with some linear algebra. We just said that SentenceBERT has been optimized for sentences, but our labels are not sentences, they're words. Ideally, we would use embedding methods that are optimized for their domain, SentenceBERT for sentences and Word2Vec for words. But this poses a problem. If we use Word2Vec embeddings for words and SentenceBERT embeddings for sentences, these embedding spaces know nothing about each other. We can't use cosine similarity between document representations and label representations when those representations live in different spaces. We need a map that converts one space to the other. And we can build that map. To do so, we'll take a bunch of words and generate SentenceBERT embeddings and Word2Vec embeddings for each one of them. Next, we'll perform a least squares linear regression with L2 regularization between the SentenceBERT representations and the Word2Vec representations, thus mapping words in SentenceBERT space to those same words in Word2Vec space. And I'm going to call this a Z-map, for lack of a better word. Once we have this map, we can use it in our original problem, where we generate SentenceBERT representations for documents and for each of our labels. We'll then apply our Z-map to all of those embeddings, converting SentenceBERT space to Word2Vec space. This allows us to have the best of both worlds, the semantic richness of sentences from SentenceBERT, as well as from Word2Vec for words. Now we can see this explicitly through matrix multiplication. We start with SentenceBERT embeddings, one for each article we wish to classify, so that's n dimensional. SentenceBERT embeddings are 768 elements long. The Z-map we learned transforms SentenceBERT space to Word2Vec space, which is 300 elements long. So I see our Z-map here is 768 by 300. The result of this multiplication is a new matrix with one row for each of our article examples, but now the embedding for each is only 300 elements long. And now we can perform classification by maximizing the cosine similarity in this new lower dimensional space. And here are the results. We drastically improved performance on the AG News dataset, increasing classification accuracy by nearly 15 points. But we can also see that this didn't result in better performance for our other dataset, classifying Reddit posts by their subreddit, and we'll come back to that. The important takeaway here is that we still haven't used any labeled data, but there are plenty of use cases in which we have some labeled data, even if it isn't as much as we might like. Let's see how we can use this general method to now incorporate labeled data. Instead of learning a mapping between words in two different embedding spaces, we'll learn a map between examples and their labels. Our goal is to learn a transformation that will rely on the semantic richness of our representation so far, which is multiplying SentenceBERT embeddings by Z, while still allowing us to incorporate information from the labeled examples. We thus perform another least squares regression between annotated articles and their labels, both first modified by ZMap, and then apply this new map, which I'll call WMap, in series, as I've shown here. Classification then proceeds as usual, maximizing the cosine similarity in this new space, which now incorporates labeled data. The results are in, and as usual, incorporating training data makes a huge difference for both data sets this time. While these results may not represent state-of-the-art performance for these data sets, this method was trained on only a few hundred examples. The fact that we're seeing nearly 80% classification accuracy on the AG News dataset after training with so few examples makes this a viable option for some use cases. Last but not least, this session wouldn't be complete without discussing the pros and cons of text representations as few-shot classifiers. This method is clearly beneficial for use cases in which only a few annotated examples exist, but perhaps more importantly, for use cases in which the labels might change over time. For example, relabeling existing categories or when new categories are added. In these cases, you wouldn't want to have to retrain a classifier on the new or reformatted labels, and this method allows that level of flexibility. But we also see this as a useful method to bootstrap a labeled data set. It's often easier for a human annotator to check whether an assigned label is correct rather than to classify from scratch. Which brings me to my next point and the drawbacks. Let's address the elephant in the room here. We showcase the experimental results of this method because we already had access to large labeled data sets. In reality, the lack of labeled data will present a significant challenge because without it, validation is next to impossible. And it's been my experience that rather than trying to get fancy attempting to validate without labeled data, that time is better served by simply spending a day or two annotating some examples, which we can do with this method. But another crucial element is that the labels must be semantically salient. They must be meaningful. This method will not work if the labels are arbitrary buckets like 1, 2, 3, etc. But in addition to being meaningful, labels must also be direct. And we can see an example of this with the Reddit dataset. Remember how I showed you that the classification accuracy on the Reddit dataset actually performed a little worse when we applied a ZMap? Well, let's talk about why. And here I show the names of the 10 subreddits that I used. Those are the labels. And for each one, I had randomly selected 1,000 examples. The colored bars show how each of our three models, SentenceBERT, SentenceBERT with ZMap, and SentenceBERT, ZMap, WMap, how each of those classified those examples. If we had had perfect classification, each bar would be exactly the same length and clock in at 1,000 examples for each category. But instead we see that many of the posts, in fact, most of them, are classified as funny. And applying a ZMap or a WMap only exacerbates the issue. This isn't necessarily the model performing incorrectly. Quite the contrary, it's doing exactly what we would expect. The word funny is so general that it can be applied as a reasonable label to lots of posts from many subreddits, and tons of human interactions are funny. So while this word is meaningful, it's also quite broad and all-encompassing. While this can be mitigated in part by allowing multiple labels for each classification, it's nevertheless an important point to note. Going back to our limitations, the last thing I want to point out is that this method probably won't beat out more sophisticated supervised classification models. Our experiments show that while some labeled examples substantially increase classification performance, these performance gains quickly plateau because the Z and W maps are simply too small to capture all the statistical relationships. If you have loads of labeled data, you're better served using standard supervised methods that can glean more from a larger pool of labeled data. And that about wraps it up. Thanks for listening, and you can learn more at the links below, including a link to the report that accompanies this presentation, a link to our GitHub repo so you can explore that demo for yourself, as well as links to our other research and reports. Thanks again.